Welcome to one of the first highlights of multivariable calculus. In this presentation, we're going to decompose the acceleration that acts on a moving object into two components. One component that is parallel to the direction of motion, that'll be the component that contributes towards the object actually speeding up or slowing down. And another component that is perpendicular to the motion, that component contributes to the object's change in direction. The central concept in the presentation actually will be that of curvature. And well, curvature is just a measure of how a curve bends. And in order to get at the curvature, we will first need to talk about arc length. Well, let's take a look. So our first goal, and that's really going to take up a large chunk of this presentation, is that we want to measure how much a curve is bent. If we're looking, for example, at this ellipse, well, just looking at it, we can see that the ellipse is bent more strongly here than it is here, because this curve is steeper than that curve. And if we send a particle traveling around that ellipse using the regular parametrization, where we're going at uniform angular speed. Now, this is not uniform velocity, and it's also not the way a planet would go around the sun, for example. This is just a standard parametrization. But what we can see here is the green vector in the animation is the velocity vector, and the purple vector is the acceleration. That is something that we can compute just taking the derivatives. And what we can see is that the acceleration vector is longer in the steep part of the curve than it is in the not so steep part of the curve, and that's because you take more acceleration to go around a steep curve at the same speed than you would going around a shallow curve. Okay, so you might suggest here that a measure of how much the curve is bent is how much acceleration we need to go around the curve. But we have to be careful here. Remember that the vector-valued functions are a dynamic notion. And so, for example, if I send a particle around this ellipse in such a way that it slows down for the steep part of the curve and speeds up in the not so steep part of the curve, then actually the acceleration here, where we have a lot of bending in the curve, is fairly small, whereas the acceleration in the shallow part of the curve is fairly large. So we need to, if we wanted to use the force or the acceleration that acts on the object as a measure of the curvature, we must traverse the curve at uniform speed. And because we want to talk about arbitrary curves, we can't just talk about uniform angular speed. We really need to make the speed uniform. And to get to that point, the first thing that we must measure are lengths of curves. And in order to do that, well, we first are just going to work on arc length, and we're going to approximate arc length with line segment. Well, that was an accidental click, but nonetheless, let's just run it through once. Okay, so let's just say I want to compute the perimeter of this ellipse, the length of this ellipse, the length of the path that little object had traveled in the previous two animations. Well, I can try to approximate that with straight lines, because for straight lines I know what the length is with the distance formula. And we can see that, of course, this approximation is not very good. So what we do is we use more straight lines. That gives us a better approximation, and by the time we use enough straight lines, let's stop again here, we get a pretty good approximation where the length of this blue polygon actually is pretty close to what the actual length of the curve is. And then, very much as always in calculus, as we make things finer and finer, we get a better and better approximation. This is something that can be done in 2 dimensions. It can also be done in 3 dimensions, even though in 3 dimensions, if I just go from the beginning of the end of the curve, I don't have a good approximation at all, and the first couple of polygons really don't look like the curve at all, right? I'm going across, over, across, and over. But then again, as always, as soon as we use an approximation that is fine enough, we get something that is pretty close to the actual length, because now also this blue polygon is very close to being equal to this red spiral. And if we run that all the way through, we see we get a really, really good approximation eventually. Okay, so we need to figure out a formula for that. Well, let's take an arbitrary curve in arbitrary dimensions. Here's the origin, here's a starting point, and here's the position vector for the starting point. Well, then we could just look at a line segment from the starting point to a point nearby, from that point nearby to another point nearby, from that point to another point nearby, and so on. And, well, a typical generic line segment would therefore start at a c of tk minus 1, because in order to get from A to a point to another point to another point, basically we are cutting up the time interval over which the curve develops, and so that means we've got t1, t2, and as a generic point we would use tk minus 1. And we would go to c of tk. The line segment is, of course, the distance between the two. So delta c, this little line segment, is c of tk minus c of tk minus 1. And, well, we know that displacement is approximately equal to velocity times time interval. And we would, of course, use a velocity here that is taken at a time between tk and tk minus 1, and all of a sudden we've got something that looks like it can be incorporated into a Riemann sum, right? A small delta independent variable times our function evaluated at a certain point inside the interval. And that's exactly what happens. L is ultimately the limit as we send the number of intervals to infinity, k equals 1 to n, of these little distances c of tk minus c of tk minus 1, and of course we take the norm. Well, that's the limit as n goes to infinity, k going from 1 to n, c prime of tk times tk minus 1, norm again, because this is the delta t, that's the tk minus 1, right? As we go from c of tk minus 1 to c of tk, time goes from tk minus 1 to tk. And rather than taking a c prime of tk star, I used a c prime of tk. As long as I use something inside the interval, that ought to work out. And that's, of course, nothing but a Riemann sum, right? That is just the limit as n goes to infinity, b minus a over n, if I use an equidistant partition here, of the sum k equals 1 to n c prime of tk. And that limit, if the function c prime norm is integrable, is just the integral from a to b of c prime of t norm dt. And so as a theorem, in the time from t equals a to t equals b, a particle with differentiable position function c of t travels the distance L equals integral from a to b, c prime of t norm dt. And theorem that follows right on the heels of that, okay, so this one we basically derived on the previous panel. Theorem that follows on the heels of this one, if you've got a differentiable vector valued function that is 1 to 1 on the time interval AB, meaning that function doesn't retrace its own steps. We don't have two different points, t1 and t2, so that c of t1 is equal to c of t2 and t1 is not equal to t2. If that function is 1 to 1 on the interval, then the arc length of the space curve traced by c of t between a and b is just L equals integral from a to b, integral of the norm of the velocity dt. Same formula. The only thing that changes is we've seen that in an earlier presentation, a vector valued function could retrace the same arc multiple times. By demanding that the function is 1 to 1, we exclude that explicitly, and that means that now the length really is the arc length because we're never retracing our steps. That is valid in any number of dimensions. Notice that we just worked with vectors and norms, so this works in 2 dimensions, 3 dimensions, and so on. And so, for example, in 3 dimensions, the length would be the integral from a to b of x prime, y prime, z prime norm dt, and that would be the integral of the square root of the sum of the squares. So that would be the integral from a to b square root x prime squared plus y prime squared plus z prime squared dt. What you can see here already is that these integrals will not be pleasant to compute, because you would have to compute the integral of a square root, and you don't have anything outside the square root to do substitutions, and that is characteristic actually of arc length integrals. Let's take a look at an example. We want to compute the length of the space curve traced by c of t being 5 cosine t, 3 sine t, 4 sine t, where 0 is between 0 and 2 pi, which means this thing, because we've got cosine and sine combined, will not retrace its steps, and well, at the end it's back at the starting position, but that doesn't change the length because we have only overlap in one point. Alright, so we know the formula, and the rest is just computation. Alright, so here's that thing again. Well, if I tell you the formula is you take the derivatives, square the derivatives, sum that up, and take the square root and integrate that, well, that's a lengthy process, but nonetheless, it's just computation. So the length will be the integral from 0 to 2 pi of the norm of c prime of t dt, which will be the integral from 0 to 2 pi of square root of the sum of the squares of the derivatives. So the derivative of 5 cosine t is negative 5 sine t, the derivative of 3 sine t is 3 cosine t, and the derivative of 4 sine t is 4 cosine t. So now we work out the squares. Well, so we still have an integral from 0 to 2 pi square root dt. Negative 5 sine t squared is 25 sine squared t, 3 cosine t squared is 9 cosine squared t, and 4 cosine t squared is 16 cosine squared t. And now we can add, right, so 9 plus 16 is 25, so we get integral 0 to 2 pi square root of 25 sine squared t, just copied, plus 25 cosine squared t dt. Now we know sine squared t plus cosine squared t is 1, so we end up with the integral from 0 to 2 pi square root of 25 dt, which is the integral from 0 to 2 pi of 5 dt, and that's 10 pi, and that's it. Well, I said that these integrals are hard to compute. Turned out this one wasn't so bad, but notice that we had to have an awful lot of cancellations just work out right. Much more characteristic is the following example in 2 dimensions, where we compute the length of the curve traced by the function c of t being t squared with 0 smaller equal t smaller equal 1. And that should be something that we recognize as a standard parametrization. This is nothing else but y equals x squared. So it's a standard parametrization. It's a standard parabola between 0 and 1. And so we just want to know the length of a parabola, which is a fairly simple object, from 0 to 1. All right, we know the formula. The rest is just computation. What do we have? The length is the integral from the beginning to the end, which is 0 to 1, of the norm of the derivative, which is the integral from 0 to 1 of the derivative of t is 1, so 1 squared. The derivative of t squared is 2t, so 2t squared. And that ends up being the derivative from 0 to 1, 1 plus 4t quantity squared. Yeah, great. You try to integrate that, and if you're really good, you can actually integrate that by hand. But I would recommend to use an integral table. And if we use an integral table, well, here is one. It's a little bit tiny, but if you may be able to see that this integral formula here is an integral formula x squared plus a squared taken for the square root of x squared plus a squared. So we would go ahead and magnify a little bit and just work that out. So here's the formula. As soon as the x squared is by itself, we get x over 2 square root x squared plus a squared ln x plus square root x squared plus a squared. So you can see that isn't really something that people would fall out of bed and just know that that is the formula. But either way, we have our 4 in the wrong place. So we're going to factor out a 4 here. And when we do that, we get 1/4 plus t squared, and then we take the 4 out of the square root, so we get a 2 on the outside. And now we can apply the formula for the integral table, and that is something where I don't want to work with split screens and all sorts of other things. Trust me, I've plugged the 1/4 in correctly. In fact, don't trust me. Look at your own integral table and verify that this is right. And then we need to evaluate that at 0 and 1. And again, even though I am somebody who says, look, you want to be able to work with things by hand as much as possible, come on. I mean, you can plug that in, and that's what I did here. I plugged in the 1 and I plugged in the 0. But what you realize is that doesn't help much at all. Ultimately, what you want is a number, and the length is approximately 1.4789 computed with a calculator. So one of the things that you also could have done is you could have computed this integral directly in a computer algebra system and gotten the approximation that way. So here's where the note comes in. As I mentioned before, arc length integrals are notoriously difficult, and we see now why. It's because that square root really ultimately or very quickly gets us to integrals that are not just hard to find and need to be looked up in an integral table. It leads very quickly to integrals that can't be solved by hand at all. Okay, so now let's continue talking about this conceptually, because after all we want to look at the concept of curvature and ultimately get to the acceleration. Quick insight, the arc length does not depend on the parametrization. Well, of course it doesn't, because the parametrization just tells us how fast or how slow we travel around a path. So if we're looking, for example, at the ellipse from the introduction, doesn't matter how fast or how slow I get around that ellipse, the length that I traverse in one orbit is the same whether I go fast or slow. In terms of the formula, well, the arc length is the integral from a to b of the velocity of the speed dt. And physically, well, if I have slower speed, I need more time, which means I've got a longer integral with a smaller integrand, whereas, so a longer interval. Faster speed means we need less time, so I've got a shorter interval but a larger integrand, so we've got a shorter interval dt, interval ab over a faster speed, and either way, that should be the same. So physically it makes at least a bit of sense. The formal proof is a different story, and that's because the substitutions are kind of hard there. Let's talk our way through that anyway, though. So we take c of t and u of s, be two differentiable one-to-one parametrizations of the same curve c, where a is smaller than b and d is smaller than e. Then, and this is the hard part of the proof that we're just going to quote, there will be a parametrization f of c so that u of s is c of f of s, where f of d is a and f of e is b. So basically, whenever I've got two nice parametrizations of the same curve, I can translate one parametrization into another via composition with a function that is basically a reparametrization of c. We'll call these things reparametrizations in just a second. So that would be quite tedious, and that's what we omit. Once we've got that, well, if I compute the arc length with u, I would have that the length is the integral from d to e u prime of s norm ds. And that's the integral from d to e of the derivative with respect to s of c of f of s norm ds. And I can compute that with the chain rule. That's the integral from d to e c prime of s f prime of s, but f prime because f will have to increase from a to b. As we go from a to b, f has to increase from d to e. F prime is positive, so I can pull that out. And the norm stays around the vector valued part. And now I can use the regular substitution formula and realize that this is the integral from a to b c prime of t dt. Because if I set, if I just do a substitution, t equals f of s, then well, f of d will be a, f of e will be b, and the rest from the substitution formula works out in such a way that the f prime ds is the dt, and the c prime of f of s is, of course, the c prime of t. And that's it already. All right, so arc length does not depend on the parametrization. That actually is a key insight, because now one of the things that will be very important for us as we formally define the curvature is that a reparametrization of a vector-valued function c of t is a differentiable function f of s going from an interval cd to the interval ab, so that f prime of s is greater or equal than 0 for all s. And that basically is just that now we could look at c prime of f of s, and that's what we're going to do, because the next goal is going to be to change the given speed, the speed that is natural for the parametrization that we are working with, to a speed 1. And we're going to do that by just adjusting the way our clock runs. And this is the conceptually deepest part, even though the computations work out very nicely. So basically, if we have a vector-valued function c of t, where t runs from a to b, I can define a function s of t to be the integral from a to t of the norm of the velocity of w dw. Remember, I cannot use the same variable here and here. And the meaning of this function is, of course, that this is the distance that the particle has traveled in the interval from a to t. Okay, so this function measures the distance traveled up to time t. So when s of t is equal to u, we have traveled u units. And now the key idea for the definition of the curvature, as well as for reparametrization with respect to the arc length, as this is called, is that we're going to use the distance as our new parameter. So basically, if we replace t with s inverse of u, well, if s of t is u, then t is s inverse of u. So that is something that we can do. That gives us a parametrization in which the particle moves at unit speed, because remember, u now gives us the distance traveled, and if the distance traveled is our clock, then the particle moves at unit speed. Of course, the conceptual leap here is pretty big, because what we do is we express time in terms of distance, and that is exactly backwards, right? That is pretty much the opposite of what we typically do. We typically express position in terms of time. All of a sudden, we express time in terms of distance. We have just solved our equation distance of time equals number for time equals number depending on distance. So that is something where we also see the computational power of calculus, because even though the first time, in fact probably the first few times you see this feels really strange. It still feels strange to me, and I've done this a couple of times. But the mathematics works beautifully. So that means the calculational power of calculus is works to such an extent that whether we can completely visualize this or not, we can work through the mathematics and we can get the formulas that guide the concepts out of that. And so even if it's technical, it's going to work beautifully. So let's see. Theorem. If you take the differentiable vector valued function c of t, now this has its regular undistorted time clock. We set s of t to be the distance traveled up to time t, integral a of t of the velocity dw. So that will be the function that measures the distance traveled up to time t. Well, then we let s inverse be the inverse function of that if it exists. So everything here is qualified, if we want to be completely formal, on the assumption that things really do exist, but that is something that we would worry more in an abstract math class. Typically in applications these things work out. Well then, ds dt. Well, ds dt is c prime of t. That should work, because this is just an integral with a variable upper bound, where we just have to recall the fundamental theorem of calculus in its derivative form. Well, okay, that's another one of those formulas that only comes up so often, but this is just a single variable integral, right? So that's going to work out pretty well. And we have that the derivative with respect to u of c of s inverse of u is 1. That's what I promised, right? We are now using the distance to measure our time. So if distance is time, then at time equals distance u, we will have traveled a distance of u conceptually. We're going to see how the computation works out in the proof. And if we define c arc of u to be c of s inverse of u, remember s inverse is the inverse of our time converted to distance function, then this distance along the curve, then the distance along the curve from c arc of 0 to c arc of u is u units. And the vector valued function c of s inverse of u is called the reparametrization of c of t with respect to the arc length, because we now use the arc length, which we have worked out up here, as our parameter. All right, so that is a huge conceptual theorem. Maybe hit pause right now, take a break, and think about that for a minute. We're going to work our way through the proof, which is at least going to show that the theorem is right. So, proof. ds dt is the derivative with respect to time of an integral from a to t, c prime of w norm dw. Independent of how hard our integrand is, this is an integral with a variable upper bound, so the derivative is computed using the derivative form of the fundamental theorem of calculus, which says that the derivative of an integral with variable upper bound is the integrand at the upper bound. So this is c prime of t norm as claimed. If we're now interested in the derivative, now as an intermediate step, for the next thing we want to compute, we need to find the derivative with respect to u of s inverse of u. Well, that is from the formula for derivatives of inverse functions. So again, here is where we're very deeply into this other part of multivariable calculus, which says, look, at some point in time, you just have to start looking up formulas, or better, remember them, but the derivative of the inverse function, that formula we haven't looked at in ages, so look it back up. I can tell you here it is 1 over s prime, so 1 over the derivative of the original function evaluated at the inverse function of u. And that's what we're going to use to work out the derivative with respect to u of this reparametrization with respect to the arc length of this c of s inverse of u. Well, you work out the derivative of c of s inverse of u with the chain rule, of course. So this is c prime of s inverse of u times the derivative of s inverse of u. But we know what that is, right? So this is the norm of c prime of s inverse of u of 1 over s prime of s inverse of u. But what was s prime? S prime was c prime norm. So this is c prime of s inverse of u 1 over c prime of whatever is inside, which was s inverse of u. Well, now I can pull the 1 over c prime of s inverse of u norm out. So this is 1 over c prime of s inverse of u norm times c prime of s inverse of u norm, and that's 1, which means that this derivative really is 1. And that means that the distance between c arc of 0 and c arc of u along the curve, we have that is the integral from 0 to u of c prime arc of v dv. So that would be the derivative of the reparametrization with respect to the arc length. That will be the integral from 0 to u d dv c of s prime s inverse of v norm dv. But we know what that is. We had computed that to be 1. And the integral from 0 to u of 1 is, of course, u, and that is the end of the proof. Okay, so that establishes that we can rewrite any sufficiently decent behaved parametrization in such a way that the particle travels at unit speed. Example, well, we can reparameterize the function c of t equals e to the negative t cosine t with t greater or equal than 0 with respect to the arc length. All right, we're back. Well, you notice that I took a pause here, so I'm certainly practicing what I'm preaching. If you currently feel the same characteristic headache feeling that comes from concentrating on something that is difficult, really hard, then it may be a good time to just take a quick break. But the one thing you're not going to do is quit on me, because we've got a whole lot more to do here. So let's reparameterize this thing with respect to the arc length. Of course, you know what's coming, right? I mean, s of t is the integral from 0 to t c prime of w dw, and the rest is just computation, because even though the formulas are complicated, we know what to do. It's just a bunch of steps. So let's work our way through that. The integral of c prime of w norm, well, I would have to take the square root of the sum of the squares of the components of the derivative. All right, well, the derivative of e to the negative t cosine t is negative e to the negative w cosine w, because I'm going to use w as my integration variable. And then we have plus e to the negative w times negative sine of w, which is negative e to the negative w sine of w here. So that's the product rule. And in the same way, this part here is computed from the y component of c of t using the product rule, right? Derivative of e to the negative t, negative e to the negative w now, times sine of w plus e to the negative w times the derivative of the sine function, which is cosine of w. Well, now that we have that, even though that's pretty big, the next thing to do is obvious. We have to multiply out parentheses and rings. Okay, one more time. We work this out with the binomial formula. We take the square of the first one, which is e to the negative 2w cosine squared w. We take 2 times the first times the second, and the minus signs cancel each other, and the e to the negative w becomes e to the negative 2w. Here's the cosine, here's the sine, and then we have the square of the second, e to the negative 2w sine squared w. And we're adding to that the other square, so we get square of the first, e to the negative 2w sine squared w, minus, this time that stays in because we've got a minus and a plus, 2 times the first times the second, so e to the negative w times e to the negative w is e to the negative 2w. Then we've got the cosine w and the sine w here. And finally, we square the second one, e to the negative 2w cosine squared w raised to the 1/2 dw, and we can see this term here is the same as this term here, only that the one on the bottom is negative, so those two cancel. Other than that, this one combines with that one, and this one combines with that one, and so we end up with the integral from 0 to t, 2e to the negative 2w cosine squared w, this one plus that one, plus 2e to the negative 2w sine squared w, this one plus that one. Now we realize cosine squared w plus sine squared of w will be 1, so this is actually the integral from 0 to t after we factor out the 2e to the negative 2w, square root of 2e to the negative 2w. Take the square root of that, we get that that's integral from 0 to t square root of 2e to the negative w, which is something we can compute. So that's negative square root of 2e to the negative w from 0 to t, because the antiderivative of e to the negative w is negative e to the negative w. And yeah, that is at 0, it's going to be root 2, and at t, it's negative root 2 e to the negative t. And so this is root 2 minus e to the negative, minus root 2 times e to the negative t. All right, so that's the u. Now what we need to do is we need to take our arc length, which is root 2 minus root 2 e to the negative t, and solve for t. All right, so the arc length is root 2 times quantity 1 minus e to the negative t, and we can divide by root 2. So u over root 2 is 1 minus e to the negative t. That means e to the negative t, after we bring that over and subtract the u over root 2, e to the negative t is 1 minus u over root 2. Take logarithms, we get that negative t is ln 1 minus u over root 2, and that ultimately means that t is negative ln 1 minus u over root 2, and we realize that u can only run from 0 to root 2, because after we have that we would have negative negatives inside the logarithm. Okay, well, so this is time in terms of distance, so this is the reparametrization. Now we just, okay, so u goes from 0 to root 2, and now we just have to put that in, and we get t of u being negative ln 1 minus u over root 2. We had computed that, so c of t of u will be e to the negative t of u cosine t of u, e to the negative t of u sine t of u, and if we plug that in, we get e to the ln of, well, the minus signs go away, right? So e to the ln of 1 minus u over root 2 cosine of the negative ln, and e to the ln 1 minus u over root 2 sine of that negative ln. Exponential and logarithm cancel, so this is 1 minus u over root 2 times the cosine of this big ugly thing, 1 minus u over root 2 times the sine of this big ugly thing in the y component, and that ends the computation. So on one hand, we verify again that arc length integrals are rather nasty, and reparametrizations with respect to the arc length are even nastier, even though technically speaking it's just computation, and we just have to get ourselves to the point where we can handle these computations, even if it takes a while, even if it takes several tries, and so on and so on. On the other hand, we can now also define the derivative with respect to the arc length, and the derivative with respect to the arc length is the derivative of the version of the curve that is reparametrized with respect to the arc length. So that means it's the derivative of what you would get when the particle is moving at unit speed. So it's the derivative of c of s inverse of u du, which is c prime by chain rule, c prime of s inverse of u d du of s inverse of u, which is c prime of s inverse of u, and the derivative of the inverse function is 1 over ds dt of s inverse of u, which is, of course, ds dt is c prime, and s inverse of u is still there, so this is c prime of s inverse of u divided by the norm of c prime of s inverse of u, which makes sense because if something travels at unit speed, the derivative should be a unit vector, right? As a definition that goes along with that, the unit tangent vector of the curve traced by the vector value functions c of t, note that we're staying with the original parametrization here, the unit tangent vector is dc ds of t being t of t, and that is c prime of t divided by c prime of t magnitude, so this is the unit tangent vector at time t, it is inspired by this idea that the derivative with respect to the arc length is c prime over c prime norm. We just didn't change the parametrization because, in fact, ultimately, in this section here, we're going to see to it that we can work in terms of the original parametrization. If you really don't like reparametrizations with respect to the arc length in terms of computing them, join the club. I'm part of that club too. They are a good conceptual tool, but ultimately we will try to get rid of the reparametrization with respect to u, and we will accomplish that actually. So now we can actually define the curvature. And so for a curve c of t with derivative with respect to s, denoting the derivative with respect to the arc length, we define the curvature to be the magnitude of the second derivative of c with respect to the arc length. That is, the curvature is the acceleration that is experienced by a particle that travels at unit speed along the trajectory. So it's very much this idea that I promoted at the beginning of the presentation, that curvature is basically related to the acceleration that you would experience as you travel along the curve. It's just that we've got to travel at unit speed, because if we don't travel at unit speed, then our acceleration will also depend on the velocity. Okay, so that means that our curvature is the norm of the second derivative with respect to the arc length, which is the norm of the derivative of the first derivative with respect to the arc length, which is the derivative of the unit tangent vector with respect to the arc length, where when we differentiate with respect to arc length, we also assume that the unit tangent vector is parametrized with respect to the arc length. So that's a nice conceptual formula, but it still has the reparametrization with respect to the arc length stuck inside of it. And so what we'd like to have is, we'd like to have a quicker formula. We'd like to have a formula in terms of time itself. We'd like to have a formula in terms of the original parameter. And that applies especially to the derivatives, right? We don't want to compute derivatives with respect to a variable that we don't really have a good computational handle on. Okay, so here's the curvature. It's the norm of the derivative of the unit tangent vector with respect to the arc length, which, if we use the chain rule, is the derivative of the unit tangent vector with respect to time times the derivative of time with respect to the arc length. Again, one of those concepts that doesn't feel too right, because typically we differentiate distance with respect to time, but using Leibniz differentials, or respectively the chain rule, we realize, yes, as long as we've got that inverse function available, we can differentiate time with respect to distance. And in fact, we're not going to mess with that too long, because we know from the derivative formula for inverse functions that this is the derivative of the unit tangent vector with respect to time divided by the derivative of the distance function with respect to time. And we had computed that before. That was just c prime of t norm. And of course, on the top here, we don't have any arc lengths involved anymore. So this is t prime of t norm. So, hey, purpose accomplished. We have a formula in terms of t. It is also quicker, but it's not as quick as it could be, because this one no longer involves derivatives with respect to the arc length, and it's certainly a formula that we want to commit to memory. Curvature is unit tangent vector norm divided by the speed. And so that is great. But t, well, the unit tangent vector is c prime of t divided by the speed, divided by the norm of c prime of t. That's a pretty complicated quotient. We'll have square roots in the denominator again, so we'd have to work with all sorts of ugly quotient rules, and so that derivative would not be too much fun to compute to get t, and then we'd have to take another derivative. So we'd like to abbreviate that, and in order to do that, we're going to look at c prime. So here's where we're now following a computation along, where at the end we're going to see why the computation was set up the way it was. I don't know how the formula was conceived, but this is the kind of thing that mathematicians also sometimes do. We just start writing a few things out to see where they lead us. So c prime of t, the velocity, is of course speed times velocity divided by speed. I've just multiplied by 1. but I realized that this is t, so this is just a cheap trick to get t involved. So c prime is just c prime norm times t of t. Now I can take derivatives on both sides. On the left side I get c double prime, and on the right side I get the derivative of the speed times the unit tangent vector plus the speed times the derivative of the unit tangent vector, and of course that derivative is what I want to have. Now I could try to solve for t prime of t, and it turns out that that is quite horrible, and it would still require derivatives of the speed, and it would require us working with the unit tangent vector. And so let's remember that we're actually interested in the norm of t prime of t. And so if I first multiply with something that I can ultimately go away, things shouldn't be so bad. So I'm going to multiply both sides with the unit tangent vector. On the left hand side I just get t prime, on the left side I just get t of t times cross c double prime. So I'm going to use the cross product, which in particular means the formula in terms of t only works in three-dimensional space. But nonetheless I can work that out, and I can multiply the right side also with it. And I realize, or you realize, one of the nice things that happens is t of t cross t of t, a vector cross itself, is 0. So as I multiply this out, I get c prime norm prime times t of t cross t of t, which is 0, plus c prime norm t of t cross t prime of t. And we realize that this part here goes away, which means the ugly stuff is gone. So that's nice. So that's c prime of t norm t of t cross t prime of t. And now I can take norms on both sides, and on the left side I just get t of t cross c double prime of t, and on the right side I get c prime of t, t norm, t prime norm. And that is because, remember, t prime of t, or t of t, has uniform length. T of t has always length 1. That means, by the lemma that we had in the previous presentation, that t and t prime are perpendicular to each other, and with t and t prime being perpendicular on each other, the cross product is just the product of the magnitudes, because the sine of the angle in between is the sine of 90 degrees, which is 1. Okay, and now t of t, of course, is 1, so I realize that t cross c double prime is, of course, c prime over c prime norm cross c double prime is c prime norm, as we had on the previous panel, t norm, which is 1, times t prime norm. And this is now really easy to solve for t prime norm. First of all, I just drop the 1 here, and I put this on a numerator, right? If I have that, I can just multiply c prime with c double prime and then divide by c prime norm. So I get c prime cross c double prime norm divided by c prime norm, and that's equal to c prime norm t prime norm. Well, okay, the c primes don't cancel, but we get t prime norm being c prime cross c double prime norm divided by c prime norm squared. And then the curvature is t prime norm over c prime norm, which means the curvature is c prime cross c double prime norm divided by c prime cubed. And this one is nice because all derivatives apply only to the original parametrization t. So this is a c of t. So this is a direct computation. It's tied to three-dimensional space because we use the cross product, but most of our work will be in three-dimensional or lower dimensional space, meaning two-dimensional space anyway. And remember, two-dimensional space can always be embedded into three-dimensional space by attaching an artificial z coordinate 0. Another thing that we can see here is that if we have our particle travel along this path, well, c prime cross c double prime, that basically gives you, that one gets larger the closer the angle between c prime and c double prime is to a right angle. And of course, when things bend a lot, then more and more of the acceleration will have to be invested in changing direction, which means that c double prime will be closer to being perpendicular to c prime than on something that doesn't have much curvature. So the numerator here makes a good bit of sense that that ought to be the cross product. And we're dividing by c prime of t cubed because that takes, basically that divides out the effect that the speed has on the numerator. Okay, so now let's take a look at an example. Compute the curvature of the curve traced by c of t being t e to the t e to the 2t. Well, we know the formula for the curvature. It's c prime cross c double prime norm divided by C prime norm cubed, and the rest is just computation because now we just plug it. Okay, so again, no disrespect. The computation will take a while, but it's just computation. It's stuff we know how to do. We just have to piece it together. Remember that philosophy from multivariable calculus. We've got to take all the stuff that we know and piece it together in potentially more complicated computations. So, C prime cross C double prime. Well, what would that be? C prime is 1 e to the t 2 e to the t. C double prime is the derivative of that, so it's 0 e to the t 4 e to the 2t. We have to work out the cross product and then take the norm. Well, the cross product, well, what do we get? We get e to the t times 4 e to the 2t is 4 e to the 3t minus 2 e to the 3t from here, so that's 2 e to the 3t for the first one. Second component, well, we blot out the second row and do the cross multiplication. 1 times 4 e to the 2t minus 0 gives us 4 e to the 2t, and then remember, in the middle component, we've got that extra negative sign. And finally, for the third component, we blot out the third row. 1 e to the 2t minus 0, 1 e to the t minus 0 is e to the t. Now we take the norm of that, so that would be the square root of the square of the first, which would be 4 e to the 6t, because e to the 3t squared is e to the 2 times 3t. Similarly, this becomes 16 e to the 4t, and this one squared is e to the 2t. And yeah, there isn't much else that can be done there. So we also have to look at the norm for c prime of t. Note that c prime is here, so that would be the square root of 1 squared. E to the t squared is e to the 2t, and 2e to the 2t quantity squared is 4e to the 4t. And that means now that the curvature is this entity here divided by this entity cubed. And so that's the square root of 4e to the 6t plus 16e to the 4t plus e to the 2t divided by 1 plus e to the 2t plus 4e to the 3t to the 3 halves. The half comes from the square root here, and that's the end of this one. So again, these things don't necessarily work out pretty in the sense of single variable calculus, that answers come out nice to be maybe even integers or so. The beauty in this stuff really isn't anymore in beauty of the result. The beauty in this stuff lies in the fact that we can compute it at all, that we really have a measure to determine how much a curve bends. And in order to connect that to something that we know a little bit better, let's compute the curvature of a circle of radius a. Now, what can we say if we think about a circle? Visualize a circle. Come on, that's something that you ought to be able to do. A circle bends everywhere the same way, so that curvature ought to be a constant, and it turns out to be. And so what do we have? Well, a circle of radius a, standard parametrization, is a cosine t, a sine t, and because we want to use a formula that involves a cross product, we put in the artificial z component 0. That gives us that c prime cross c double prime norm will be the cross product of derivative of a cosine t is negative a sine t. The derivative of a sine t is a cosine t. 0 stays with us. And the second derivative, the derivative of negative a sine t is negative a cosine t. The derivative of a cosine t is negative a sine t, and the 0 stays with us. And now we work out the cross product, and there's something very nice happening here, because the first component is what you get when you blot out the first row and then cross multiply the second and third. Well, that's just products that involve 0, so the first component will be 0. Second component, same story. You blot out the second row, cross multiply, you get a bunch of zeros. So the only thing we really are interested in is the third component. And the third component will blot out the third row. You get negative a sine t times negative a sine t is a squared sine squared t, minus a negative a cosine t times a cosine t, minus minus gives you plus, and you get a squared cosine squared t. Well, sine squared t plus cosine squared t is 1, so this is just the norm of 0, 0, a squared, and that is, of course, nothing but a squared. We then also need the magnitude of the velocity, we need the speed, so that's the norm of negative a sine t, a cosine t, and 0. So that's the square root of a squared sine squared t plus a squared cosine squared t from here plus 0. Sine squared t plus cosine squared t is 1, so this is the square root of a squared, which is a. And that means that the curvature is the norm of c prime cross c double prime divided by c prime norm cubed, which was a squared divided by a cubed, so the curvature is 1 over a. So that's done. Does that make sense? Well, first of all, it is a constant, which is what we would want to expect, because a circle bends equally anywhere we look at the circle. And A is the radius. Well, a circle with a tiny radius actually has a lot of curvature, because that's a really tight curve, whereas a circle with a large radius, or something that has a circular cross-section with large radius, such as the Earth, doesn't have much curvature, because people for a long time thought that the Earth was flat, right? And that's because the curvature isn't that big. So that makes sense. Large radius, small curvature, small radius, large curvature. So now we come to the physics part of this presentation. So up to here we have talked about geometry, even though we used kinematic reasoning to arrive at the geometric quantities. What we want to do now is we want to analyze what happens when a particle travels along a curved path under an acceleration a. Well, what happens there is the acceleration will decompose into a component that is parallel to the direction of motion, and that parallel component contributes to the change in speed. And so it should not be too surprising, we haven't arrived at yet, but we will, that this component is derivative of the speed, v prime, I'm using the physics convention, right? V is the velocity, and without the arrow it's the speed, v prime times the unit tangent vector, so that magnitude really is just the derivative of the speed. And then there is another component. That component is perpendicular to the direction of motion. It doesn't do any work, but it causes a change in direction. And that component, that normal component, is going to be, we're going to derive that that's kappa speed squared times n, where n, this unit normal vector, is t prime of t divided by the norm of t prime of t. So it certainly is a unit vector, and we're going to see, and we know that it is perpendicular to t because t and t prime are perpendicular to each other, because the derivative of t, the magnitude of the derivative of t is 0. And so that means that n really is perpendicular. And we can see that the normal component of the acceleration is kappa times speed squared, which means if you've got a lot of speed, of course, it will take a lot of acceleration to get you around the corner. And other than that, the acceleration is proportional to the curvature, which also makes sense. It takes more acceleration to go around a tight curve. You have more sideways forces around a tight curve than you have around a curve that is not so tight. How do we work that out? Well, we look at the unit tangent vector, and that is c prime of t over c prime of t norm. So that's certainly not something that you want to differentiate. So that's velocity divided by speed. And that means that the velocity is speed times unit tangent vector, right? So the physics convention, this is a vector, this is a scalar, because we dropped the vector notation. Now I can take the derivative of that, and I will get the acceleration. So the acceleration is the derivative of the velocity, which by product rule is speed prime times unit tangent vector plus speed times the derivative of the unit tangent vector. So now we just have to work out the derivative of the unit tangent vector. But so we've got speed prime unit tangent vector. Well, what can we say here? We're going to reduce that to the curvature, right? So we keep the speed. T prime of t is of course the same as t prime of t if we divide it by its norm and multiply with the norm. We know, let's see, and right now I'm so tired I don't remember my formulas. Okay, t prime of t divided by t prime of t norm, that is that unit normal vector. And t prime of t norm, remember that kappa was t prime of t norm divided by c prime norm. So if we solve that for t prime, we get that we keep the first part, we keep the velocity. T prime norm is nothing but kappa times c prime norm. T prime over t prime norm is kept. C prime norm, of course, is nothing but the speed, it's v of t. And so that means that this is v prime times t plus v prime plus speed squared, because this is v of t and this is v of t, times kappa of t times that unit normal vector, and that is already the decomposition of the acceleration as promised in the previous picture. Alright, obviously this one is spliced in, and I was debating with myself whether I should just do a smooth splice in or whether I should really start talking to you here one more time, and I decided, oh, we ought to talk. Now, this presentation already has been quite long, and so if you want to take a break before we continue, please do so. The example that we're about to see is a computation of the components of the acceleration for a particle on a certain path. Very natural follow-up to, of course, deriving these formulas. And it is something that I initially hadn't planned because basically I think people in education for generations have always hoped that after you teach people how to do the individual pieces of something, people put them together. And technically, that's not that much of a problem, except that as you put pieces on top of pieces on top of pieces on top of pieces, ultimately it just gets too long. And if you have been trained to do the individual pieces, well, there's of course the possibility that a longer problem leads to making mistakes, but there's also a certain insecurity because all of a sudden the problem takes longer than it used to. And this is not something that is limited to students who have trouble with computation. Even people who have very little trouble with computation, when it comes to these longer ones, can get bogged down simply because the computations are that long. I have just seen that. I've taught a class with the flipped format where the students watch the videos and then come to class, and it was a great class. We had a lot of fun, good kids. I think it was quite a success. But the components of acceleration were one of those things where I thought, well, we've got the formula, okay, so now we just have to plug into the formula. That once you've done it a couple of times, it really isn't that hard. And so I didn't give any examples, and performance on the test problem wasn't that good. And that's unfortunate, of course, because it was a test. And it is also unfortunate in the sense that the components of the acceleration are certainly conceptually very important. They are an important application, as well as they are a nice computation that allows us to test just about everything we've done here. So take this example seriously. You've already been talked to, hopefully not perceived as talked at by me for quite a while in this presentation. So if necessary, take a quick break, and then we're going to take a look at how to do the computation. It's not that hard. It's just that it's a lot of details. It gets tedious, but that's something we have to get used to, because as we are approaching reality more and more, and essentially the components of the acceleration are a way in which reality is modeled in dynamics, as we do that, because reality is complicated, computations will get longer, such as this one. All right, let's have a look here. So the example is that we want to find the normal and tangential components a(n) and at of the acceleration of a particle with position vectors c of t being t, t squared, and t cubed when the particle is at the point 2, 4, 8. It's just computation, nothing else. However, the computations take some time, and so we really should go over them in detail, especially in light of what I have seen. This is something where really where people at my end of the educational business simply have to realize that just because we can put the pieces together now, because we've done it for a couple of decades, does not mean that it is automatic. We probably have sweated through that quite a bit themselves when we were in your seat. It's just that at some point in time, memory pushes that pain away. Alright, so the big key really is organization. We just have to do all these steps. We have the formulas, it's just that the formulas have a lot of ingredients. So, we start with the fact that, well, we know that c of t is t, t squared, t cubed. For the normal and tangential components of the acceleration, we will certainly need the velocity and the acceleration. Well, so c prime of t will be 1, 2t, and 3t squared. And we need the acceleration itself, which will be 0, 2, and 6t, right here as c double prime. And now, from that, we can figure out the speed. We can figure out v of t without the vector arrow, so that's not the velocity, that's the magnitude of the velocity. And so that's the magnitude of 1, 2t, 3t squared, which will be square root of 1 plus 4t squared plus 9t to the fourth, square root of 1 plus 4t squared plus 9t to the fourth. Again, just very simple computation, right? We know that the speed is the magnitude of the velocity. We know how to compute velocities and all that, but what at the beginning of our work with vectors may have been a separate problem, compute the magnitude of such and such a vector, all of a sudden is now a part of something that takes a whole lot longer and involves a parameter t. Okay, so we've got v of t. We will need c prime cross c double prime magnitude for the curvature, because the curvature is part of the normal component of the acceleration. And so that would be c prime, which was 1, 2t, 3t squared, cross 0, 2, and 6t, which was c double prime. And if we compute that cross product, well, okay, so that would be 12t squared minus 6t squared, so that'll be 6t squared at the top. 6t minus 0 is 6t, with the extra negative sign is negative 6t. And then we get 2 minus 0 is 2 for the z component. And if we take the magnitude of that, we get the square root of 6t squared quantity squared is 36t to the fourth. Negative 6t quantity squared is 36t squared. 2 squared is 4, so we get the square root of 36t to the fourth plus 36t squared plus 4. Again, not something that we can't do, not something that's hard, but again, this would have been a separate problem earlier on, and here it's again just a piece of something a lot larger. And so now the curvature, well, the curvature is c prime cross c double prime magnitude divided by c prime magnitude cubed. So it ends up being this square root here, which is what we had obtained for c prime cross c double prime magnitude, divided by the cube of the speed, which is what we have here, right? So just big ugly formula, and we're not going to simplify too much, because actually I don't think there is much we could do here. We could take the 4 out of the square root, but that really wouldn't do that much either. Either way, this gives us the curvature. All right, so what do we need now? Well, for the normal component of the acceleration, we know that that is curvature times the square of the speed, so it'll be what we had computed for the curvature times the square of what we had computed for the speed, and then of course that's a quick cancellation here. The square cancels with the cube and just leaves us the square root in the denominator. So the curvature, the normal component of the acceleration at time t is square root 36t to the fourth plus 36t squared plus 4 divided by square root of 1 plus 4t squared plus 9t to the fourth. If we're looking at the tangential component of the acceleration, that was the derivative of the speed, and so that'll be the derivative with respect to time of this thing that gives us the speed of this square root. So it's the derivative with respect to t of square root 1 plus 4t squared plus 9t to the fourth. And the derivative of a square root is 1 over 2 times square root of whatever was inside, which is the 1 plus 4t squared plus 9t to the fourth, times chain rule, derivative of the inside 8t plus 36t cubed. And so that simplifies just a little bit, because the 2 cancels with the 8 and the 36 here. 8 over 2 is 4, so we get 4t. 36 over 2 is 18, so we get 18t to the third, and the square root stays in the denominator. And so that is the normal component and the tangential component of the acceleration at time t. And again here, a little trip up, of course, is that we know that the tangential component of the acceleration is the derivative of the speed, but that means we just have to read that right. This is not that we take the velocity vector and take the derivative of that again, because that would be the acceleration vector. We take the derivative of the speed formula, if you will, of the scalar speed. And again, we are not done, because we are actually interested in those things as numbers that we obtain when the particle is at the point 248. Okay, so we continue and we realize that if c of t is t squared t cubed, then we have to set that equal to 248 to obtain our parameter t. And of course, that's really easy. The first row already tells us that t has to be equal to 2. The remaining rows are sanity checks, because as soon as we know that t must be equal to 2, the other equations must be satisfied also, because otherwise the particle never reaches the point 248. But of course, 2 squared is 4 and 2 cubed is 8, so that works out very nicely. And so that means that we now figure out an of 2, which means we plug in 2 into that big old ugly formula we had on the previous panel. And so that's 36 times 2 to the fourth plus 36 times 2 squared plus 4. Is there a nice way to work that out? Let's see. 2 to the fourth is 16. 2 squared is 4. So this is just 20 times 36, which is 720 plus 4. So the numerator should be square root of 724. Hey! And the denominator, well, similar story here. Let's see. 2 to the fourth is 16. So we get 9 times 16 plus 4 times 4 is another 16. So that's 10 times 16 plus 1. So that's square root of 161 in the denominator. And that's approximately 2.1206. There is nothing else I want to do with that. I don't want to simplify that any further, and maybe I should have used the calculator right away. And for the tangential component of the acceleration at 2, we realize that that is 4 times 2 plus 18 times 2 cubed divided by square root of 1 plus 4 times 2 squared plus 9 times 2 to the fourth, which we already had. So the denominator will be square root of 161. And then we have, let's see, 18 times 8. That would be 80 plus 64 is 144 plus 8 is 152. Ha! I got it right. And that, of course, if you want to have the number, you work that out with a calculator. That's approximately 11.9793. And that's the end of this example. So, what have you seen here? You have seen, hopefully, exactly what I've promised you. There is nothing in this computation that you can't do. You just have to organize it right. You have to puzzle it apart in such a way that ultimately all of it makes sense and all of it terminates correctly. That, of course, takes some time, and if this is the first time that you have to do that, then yes, it is something that takes some getting used to, and then it really isn't bad to throw out an example like we have done here. And with that, we return you to our regularly scheduled program that was already in progress. I'll see you. Alright, corollary out of that, the magnitude of the central force required to keep a particle on a circular path at uniform speed. That's a formula that you may remember from physics class, and it's not a bad formula to remember, just as the components of the acceleration probably should be committed to memory. But that particle going around at uniform speed, that centripetal force, right, that force that keeps that particle there, is Fc equals mv squared over r. Well, the m comes from F being mass times acceleration, v is the speed, and r is the radius of the circle. How does that work out? So r is the radius of the circle, m is the mass of the particle, and v is the speed. How does that come about? Well, we now have something that can verify that the formula is true and show some consistency with things that you may have seen derived differently in a physics class, because the normal component of the acceleration of a particle, which is the centripetal acceleration that leads to the centripetal force, that's the component that keeps the particle on the circular path, that component has magnitude kappa times v squared, and the curvature of a circle of radius r we had just worked out is 1 over r, which means the normal component of the acceleration based by what we have just worked out is v squared over r. And by Newton's first law, the centripetal force to cause the acceleration then is mass times acceleration, which is mv squared over r. Okay, if you're tired right now, join the club. I am too. This was a lot to talk about, even if you already know it. What you want to keep in mind here is that you can work your way through these derivations if necessary, even if they're hard. What's going to be assessed most likely is things like computing curvatures, computing arc lengths, computing reparametrizations, computing tangential and normal components of acceleration. So those are exactly the kinds of formulas that are probably worth memorizing. Arc length, curvature as t prime norm over c prime norm, curvature as c cross c double prime norm divided by c prime norm cubed, tangential component of the acceleration, which is v prime, speed, derivative of the speed, normal component of the acceleration, which is v squared times kappa. And so that's 5 formulas to know here, but you can see the real meat in the whole thing are the concepts, because that's what gave us the formulas. plugging into the formulas will still be tedious. Let's not poo-poo that in any way. And so those computations, if they don't work out right away, hey, that happens to me too. But it's not something that is a difficulty in principle. And with that, we have taken care of one of the first highlights in this course. Enjoy the homework, and I really mean that. This is cool stuff, this is fun stuff to do, and the practice in the computation will only make you stronger for future classes, such as further physics classes, classes in mechanics, classes in dynamics. All right, thanks.